Let's look a little bit more at independent events. Remember again that an intersection is when both of the events occur, so this would be like an AND problem. Independent events are ones where the outcome of one does not affect the probability of the other, like in that first example. One way to think about this in symbols is if the two events are independent, then the probability that the second event occurs, given, remember this bar is conditional, given that the first event occurred, should really just equal the probability of the second event. If they're independent, then the fact that the second one occurred should have no impact. And for that matter, both of these things should also be equal to this right here. Do you understand what that means? This is the probability that the second event occurred, given that the first one did not occur. All three of these should be the same, whether the first event occurs, doesn't occur, or is just completely left out, should have no impact if the events truly are independent. Mathematically, what this means is that to find the intersection's probability, we just need to multiply. So this is what you found in that warm-up problem. Let's look at an example with independent events. Here we have two marksmen firing at a target simultaneously. This is important. What we're to deduce from this is that if they're both firing at the exact same time, then whether the first person hits the target or not shouldn't affect the second person because the second person has already fired at the same time. So they're including this word to tell us that we should treat these events as if they are independent. They give us probabilities for each person hitting the target. And so let's just kind of define some variables here. Let's say that if Jiri hits 70% of the time, then this right here would be P of J, although of course we'll write it as 0.7. And if Benita hits 80% of the time, then this would be P of B, where B is the event that Benita hits the target, and that's going to be 0.8. So the first question they ask is, what's the probability that they both hit the target? In symbols, they could have written this as something like P of J and B, both successes. Since the events are independent, all we have to do is multiply those separate probabilities. 0.7 times 0.8 gives us 0.56, or 56% of the time that they will both hit the target. Moving on to the next one, pause for a minute and see if you can answer the remaining three questions by using the same logic. Look now at these results for parts B, C, and D. In each case, we're multiplying two different numbers based on who's hitting and who's missing. So something like J apostrophe would often be read as J not. And what that means here is that Jiri has not hit the target. Benita has not hit the target, so I've got both of those complement numbers. Jiri hits and not Benita, not Jiri and yes Benita, so we've multiplied these all out, gotten these results. Let me just say a few things about these results. First off, I didn't leave myself very much space here, but it would have been better if I had stated these answers as percentages. The only reason that really matters is because it would have matched what was stated in the original problem. So 56%, 6%, 14%, 24%. Another thing to notice is right here we've covered all four possible outcomes, and all of this adds up to 1 or 100%. If you were to think about a Venn diagram with the four distinct regions, let's say this circle represents all the times that Jiri hits the target. This circle represents all the times that Benita hits the target. Question A would refer to this region. Question B would refer to this region where they both miss. Question C, we're in the Jiri circle but not in the Benita circle, so that would be here. And question D refers to this region. So they should